You think you understand the atom. You've seen the image, electrons spinning around a nucleus like tiny planets around a sun. Clean, simple, almost obvious. But in 1913, when a 27-year-old Danish physicist named Niels Bohr proposed this model, it wasn't obvious at all. It was insane. It broke every rule physics had established, and yet it worked. The hydrogen spectrum glowed with 4 visible lines, 656 nanometers, 486, 434, 410. Every scientist could see them. Nobody could explain them. Then Bohr wrote 3 papers that summer, published in Philosophical Magazine in July, September, and November. Those papers didn't just describe atoms. They rewrote reality at the smallest scale. The genius wasn't in making atoms simpler. The genius was in making them quantum. If you value documented physics and atomic history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual. Using sources from the CERN Historical Archives published in their July 2013 Centenary Retrospective and the Niels Bohr Archives Complete Collected Works Volumes 2 and 3 covering 1912 to 1923, which document his original correspondence with Rutherford in the development of quantum theory through primary source letters and calculations. Now back to the information. Before Bohr, there was chaos, not the fun kind. The kind where your entire field of study is about to collapse. Picture this: 1911, Manchester, England, Ernest Rutherford's laboratory. The previous year, Rutherford and his team had fired alpha particles at gold foil. Most went straight through, but 1 in every 8,000 bounced backward. Rutherford later said it was like firing a 15-inch naval shell at tissue paper and having it come back and hit you. That single result killed the plum pudding model of the atom. J. Thomson's idea that positive charge spread evenly through atomic space like jam in a pastry, dead. Rutherford announced in March 1911 that atoms had a nucleus. Tiny, dense, positive, 10,000 times smaller than the atom itself. The nucleus held almost all the mass. Everything else, empty space, you, your phone, the ground beneath you, 99.9999% nothing. But this created a fatal problem. According to James Clerk Maxwell's equations from the 1860s, any charged particle that accelerates must radiate energy. An electron orbiting a nucleus is constantly changing direction, constantly accelerating. By the laws of classical physics, it should radiate energy continuously and spiral into the nucleus in about 100 millionth of a second. Every atom in the universe should collapse instantly. They don't. Why? Nobody knew. Rutherford himself didn't have an answer. He published his nuclear model without addressing electron behavior at all. The atom was stable, but the math said it shouldn't exist. Enter Niels Henrik David Bohr, born October 7th, 1885, in Copenhagen. Son of a physiology professor, gifted soccer player, completed his PhD in 1911 on electron theory of metals. In September 1911, he arrived at Cambridge on a fellowship to work with J. Thomson. It went badly. Thomson ignored him. Bohr's English was weak. His ideas seemed strange. By December 1911, Bohr was looking for an exit. He found it in Manchester. Rutherford had invited him for a 6-month stay starting in March 1912. That half year changed physics forever. Rutherford's lab was electric. Hans Geiger was there. Ernest Marsden, who'd done the gold foil bombardment work. Georg von Hevesy, Charles Galton Darwin, grandson of the famous Darwin, and Henry Mosley, who would soon revolutionize the periodic table. Bohr absorbed everything. Rutherford's nuclear model. Darwin's recent paper on alpha particle collisions with electrons, which suggested hydrogen had only 1 electron, not a pair. The energy calculations, the scattering data. By July 1912, Bohr returned to Denmark to marry Margrethe Nørlund. They honeymooned in England and Scotland. When he came back to Copenhagen, he became a lecturer in thermodynamics, and he started thinking about Rutherford's atom in a way nobody else had. Classical physics said the atom should collapse, but quantum physics, this bizarre new idea that energy came in chunks, said maybe it didn't have to. Max Planck had proposed in December 1900 that electromagnetic energy could only be emitted in discrete packets. He called them quanta. The energy of each quantum was the frequency of radiation multiplied by a tiny constant, 6.626 times 10 to the negative 34th joule seconds. Planck himself thought this was just a mathematical trick. He hoped it would prove unnecessary. But in 1905, Albert Einstein used Planck's idea to explain the photoelectric effect, why light hitting metal could eject electrons. Light wasn't continuous. It came in particles. photons. By 1912, quantum theory was real, even if nobody liked it. Bohr saw the connection. If energy is quantized, if it only comes in specific chunks, then maybe electron orbits are quantized too. Maybe electrons can't spiral inward continuously because there's no continuous path. Maybe they can only occupy certain orbits, fixed orbits, stationary states, and maybe when they jump from one orbit to another, they emit or absorb light in exact quanta matching the energy difference. This wasn't physics, as anyone knew it. This was a guess, a hunch, but Bohr played it. Then in February 1913, something clicked. Bohr's colleague, Hans Marius Hansen, mentioned the Balmer series to him. This was a formula discovered in 1885 by a 60-year-old Swiss mathematics teacher named Johann Jakob Balmer. He'd been analyzing the visible spectral lines of hydrogen, those 4 precise wavelengths glowing in discharge tubes. Balmer found they fit a simple pattern. Wavelength equals a constant times m squared divided by m squared minus 4. Set m equal to 3, you get the first line at 656.21 nanometers, the red one. Set m equal to 4, you get 486.13 nanometers, aqua. 5 gives 434.05, blue. 6 gives 410.17, violet. The constant was 3,645.6 times 10 to the negative 7th millimeters. Balmer called this the fundamental number of hydrogen. He had no idea why it worked. It was pure pattern recognition. In 1888, Johannes Rydberg generalized it into the Rydberg formula, which covered all hydrogen spectral series, not just the visible ones, but still, nobody knew why. Then Bohr heard about it in early 1913 and everything became clear. If electrons occupied orbits with specific energies, and if they jumped between them, the energy of emitted light would equal the difference between orbital energies. Using Planck's equation, energy equals Planck's constant times frequency. And using Einstein's mass energy ideas, Bohr could calculate orbital energies from first principles. When he did the math, out popped the Rydberg formula. Not as an empirical guess, as a consequence of quantum orbits, Bohr worked at incredible speed. By March 1913, he had a draft. He sent it to Rutherford. Rutherford was supportive but concerned. The paper was long, dense, speculative. He wanted Bohr to cut it down, make it clearer. Bohr refused. These ideas needed space. In July 1913, the first paper appeared in Philosophical Magazine, 25 pages. Title? On the Constitution of Atoms and Molecules. It opened with Rutherford's nuclear model and immediately pivoted to the problem. Classical mechanics couldn't explain atomic stabilities or spectral lines. Quantum theory could. Bohr laid out his postulates. First, an electron can move in certain stationary orbits without radiating energy, even though classical physics says it should. Second, an atom can only absorb or emit radiation when an electron jumps between stationary states. The energy of that radiation equals the difference between the two states. Third, the stationary orbits are determined by a quantum condition on angular momentum. The angular momentum of an electron in orbit must be an integer multiple of Planck's constant divided by 2 pi. Fourth, when the atom is in a state corresponding to maximum emitted energy, the orbital radius is determined by this quantum rule. For hydrogen, the ground state, the lowest energy orbit, has n equals 1. The electron sits at a radius of 0.0529 nanometers. This is the Bohr radius. At this distance, the electron is bound to the nucleus with an energy of 13.6 electron volts. To knock the electron free, to ionize the atom, you need exactly that much energy. The next orbit has n equals 2, radius 4 times larger, energy 1/4 as much. The orbit with n equals 3 has radius 9 times the ground state and energy 1/9, and so on. Each orbit is a perfect circle. Each has a precise energy, no intermediate values allowed. When an electron jumps from n equals 3 to n equals 2, it emits light with a wavelength of 656.21 nanometers, red. This is the H-alpha line astronomers use to map hydrogen across the universe. When it jumps from 4 to 2, you get H-beta at 486 nanometers. From 5 to 2, H-gamma at 434. From 6 to 2, H-delta at 410. The entire Balmer series falls out of the math. Perfectly. Bohr didn't just explain the spectrum, he predicted it from first principles using 2 fundamental constants, Planck's constant and the electron mass and charge. The second and third papers followed in September and November 1913. They extended the model to molecules, to ionized atoms, to multi-electron systems. They discussed the periodic table. They explored how chemical properties arise from electron shell structure. But the first paper was the bombshell. By the end of 1913, Bohr's model was public. The response was mixed. Some physicists were excited. Most were skeptical. The model was too ad hoc. Why could electrons only occupy certain orbits? Why didn't they radiate in those orbits? Bohr had no mechanism, just rules. Quantum rules that worked but felt like magic. Then the evidence started coming. April 24th, 1914, Berlin. The German Physical Society, James Franck and Gustav Hertz, presented results from a strange experiment. They'd built a vacuum tube with mercury vapor. They fired electrons through it. At low voltages, electrons passed through with barely any energy loss. But at 4.9 volts, something dramatic happened. Electrons lost almost all their kinetic energy in collisions with mercury atoms. Not 4.8 volts, not 5.0 volts, exactly 4.9. Every time. Then the current dropped sharply, increased the voltage more, and the current peaked again at 9.8 volts, then at 14.7. Multiples of 4.9, each collision cost the same energy. Franck and Hertz thought they were measuring ionization. They weren't even aware of Bohr's papers. Nobody in Berlin had discussed them in the physics colloquium. But other scientists immediately saw the truth. The electrons were exciting mercury atoms from the ground state to the first excited state. The energy gap was 4.9 electron volts. Discrete, quantized, exactly as Bohr predicted. In May 1914, Franck and Hertz published a second paper showing that excited mercury atoms emitted ultraviolet light at 254 nanometers. Using Einstein's photon relation and Planck's constant, this wavelength corresponds to an energy of 4.84 electron volts, almost exactly the collision energy. The atoms absorbed energy in quantum jumps and released it as photons. Bohr's model predicted it. Franck and Hertz measured it. By 1915, even the skeptics had to pay attention. But the most dramatic confirmation came from Henry Mosley. Young, brilliant, 26 years old in 1913. He'd been working in Rutherford's lab since 1910, arriving just weeks before Rutherford published the nuclear model. In early 1913, Mosley started measuring X-ray spectra. He bombarded different elements with cathode rays and measured the wavelengths of X-rays they emitted using the Bragg diffraction technique developed by William Henry Bragg and his son, William Lawrence Bragg. The Braggs had shown in 1912 that X-rays diffract through crystals at angles determined by the wavelength and crystal spacing. This made precise X-ray spectroscopy possible for the first time. Mosley tested elements from calcium, atomic number 20, to zinc, atomic number 30. He found something extraordinary. The frequency of the emitted X-rays wasn't random. It wasn't proportional to atomic weight. It was proportional to the square of the atomic number -1. Mosley's law, published in December 1913 in Philosophical Magazine, stated that the square root of X-ray frequency equals a constant times the quantity atomic number -1. The relationship was linear, perfect. Mosley had discovered that atomic number wasn't just an arbitrary position in the periodic table. It was a physical property. The number of positive charges in the nucleus, the number of protons. This mattered because Dmitri Mendelev's periodic table from 1869 arranged elements by atomic weight. But in 3 places, argon potassium, cobalt nickel, tellurium iodine, chemical properties demanded reversing the weight order. Nobody understood why. Mosley's work explained it. Chemical properties depend on the number of protons, not the mass. Cobalt has atomic number 27, nickel 28. Cobalt is heavier, but it comes first because it has fewer protons. The periodic table suddenly made sense, and Mosley's X-ray data fit Bohr's quantum energy levels. Niels Bohr himself said in 1962 that Rutherford's work wasn't taken seriously until Mosley's measurements. That was the great change. In 1914, Mosley published a second paper confirming atomic number equals nuclear charge. He identified gaps in the periodic table at positions 43, 61, and 75, elements not yet discovered: technetium, promethium, rhenium. All later found, but Mosley never saw it. When World War I began in August 1914, he enlisted with the Royal Engineers despite being an aristocrat and scientist who could have avoided service. His family begged him not to go. He felt it was his duty. Mosley deployed to Gallipoli in Turkey in April 1915 as a telecommunications officer. On August 10, 1915, during a bloody battle, a Turkish sniper shot him. He was 27. The loss was catastrophic. Many believe Mosley would have won a Nobel Prize. Some think he would have been the greatest physicist of his generation. But his work had already validated Bohr's model beyond dispute. The Bohr model explained hydrogen perfectly, but it struggled with helium, the next simplest atom. With 2 electrons, the interactions became too complex. The model couldn't predict helium's spectrum accurately. For larger atoms, the problems multiplied. By 1916, Arnold Sommerfeld extended Bohr's model to include elliptical orbits, not just circular ones. This improved accuracy for some atoms, but added more arbitrary rules. The model was becoming a patchwork. Every fix required another quantum condition, yet the core insight held electrons occupy discrete energy levels. They jump between levels by emitting or absorbing photons. Energy is quantized. These ideas were right, even though the circular orbit picture was wrong. In 1922, Bohr won the Nobel Prize in Physics for his services in the investigation of the structure of atoms and of the radiation emanating from them. The Nobel Committee recognized both the trilogy and his leading role in quantum mechanics. For his lecture, Bohr gave a comprehensive survey of atomic structure, including the correspondence principle he'd formulated. This principle stated that quantum behavior reproduces classical physics in the limit of large quantum numbers. At human scales, the quantum jumps become so small and numerous they blur into continuity. By the early 1920s, Bohr was building the Institute for Theoretical Physics in Copenhagen, funded by the Carlsberg Brewery. It became the center of quantum research. Physicists from across Europe came to work with Bohr: Werner Heisenberg, Wolfgang Pauli, Paul Dirac, Erwin Schrödinger. Between 1925 and 1928, these physicists developed full quantum mechanics. Heisenberg introduced matrix mechanics in 1925. Schrödinger developed wave mechanics in 1926. Dirac unified them in 1928 and incorporated relativity. The Bohr model was superseded. Electrons weren't particles in orbits, they were wave functions. Probability clouds. You couldn't say where an electron was, only where it might be found. The modern picture is weirder than Bohr imagined. Electrons exist in orbitals defined by quantum numbers. Principal quantum number n determines energy. Angular momentum quantum number L determines orbital shape. Magnetic quantum number m determines spatial orientation. Spin quantum number s is plus or minus 1/2. The Pauli exclusion principle, formulated by Wolfgang Pauli in 1925, states that no 2 electrons can have identical quantum numbers. This explains the periodic table. The first shell holds 2 electrons, 1 spin up, 1 spin down. The second shell holds 8, the third holds 18, though filling order gets complicated due to energy overlap. Chemistry emerges from these quantum rules, but Bohr's contribution remains foundational. He showed that quantum theory applies to atoms. He connected atomic structure to spectral lines. He demonstrated that energy is quantized at the smallest scales. His model was a bridge, classical physics on one side, full quantum mechanics on the other. Bohr walked across first. The legacy extends beyond physics. Bohr pioneered the idea of complementarity, that systems can exhibit contradictory properties depending on how you measure them. Light behaves as waves in diffraction experiments and particles in photoelectric experiments. Both descriptions are necessary. Neither is complete alone. This philosophical approach influenced not just physics, but biology, psychology, linguistics. The idea that truth depends on context, that complementary perspectives reveal different aspects of reality, that measurement affects the measured. These are Bohr's intellectual descendants. During World War II, Bohr remained in Denmark initially, despite Nazi occupation. He opposed the regime openly. In 1943, warned of imminent arrest, he escaped to Sweden, then Britain, then the United States. He worked briefly on the Manhattan Project, but spent most of his effort advocating for international control of nuclear weapons. After the war, he promoted peaceful uses of atomic energy and founded the Nordic Institute for Theoretical Physics. He continued working until his death on November 18th, 1962, at age 77. The Bohr model persists in education because it's intuitive. Students grasp electrons orbiting like planets immediately. The image is wrong. Electrons don't orbit, but it conveys essential truths. Energy levels are discrete. Quantum jumps are real. Light emission correlates with energy differences. For hydrogen, the Bohr model gives the right answers. For pedagogical purposes, it's unbeatable. The modern atom is too abstract to visualize easily. The Bohr atom is wrong in details, but right in spirit. Consider the scale. The nucleus is 10 to the negative 15 meters across. The atom is 10 to the negative 10 meters. That's 100,000 times difference. If the nucleus were a marble 1 centimeter wide, the atom would be a kilometer across, almost entirely empty. The electron probability cloud fills that space, but the electron itself, if it can even be said to have a size, is far smaller than the nucleus. Matter is mostly void. You are mostly nothing. And yet atoms bond to form molecules. Molecules combine into cells. Cells build bodies. Bodies create consciousness. all from quantum rules governing particles smaller than you can imagine, separated by distances vaster than the particles themselves. Bohr understood one piece of this puzzle. He figured out that electrons in atoms don't follow classical rules. They follow quantum rules. Energy is discrete. Transitions are abrupt. There's no smooth path from one state to another. An electron in the n equals 3 orbit doesn't gradually drift to n equals 2. It jumps instantaneously. Quantum leap isn't a metaphor. It's literal. The electron is in one state, then it's in another. The transition takes 0 time. Where's the electron during the jump? The question has no answer. The electron isn't anywhere during the jump because during is a classical concept that doesn't apply. Quantum mechanics operates outside our intuition. This was the genius of Bohr. Not that he had the final theory. He didn't. His model was replaced within 15 years. But he had the courage to say atoms don't behave classically, and here are the new rules. He didn't know why the rules worked, he just knew they did. That's empirical physics at its best. Observe, quantify, predict. The explanation comes later. The specific numbers matter. Bohr calculated that the ground state energy of hydrogen is negative 13.6 electron volts. Negative because the electron is bound. You need to add energy to free it. This number, 13.6 eVas, is the Rydberg constant in energy units. Every hydrogen spectral series relates to it. The Lyman series, discovered in 1906 by Theodore Lyman, involves electrons jumping to n equals 1. These transitions emit ultraviolet light. The Paschen series, found by Friedrich Paschen in 1908, involves jumps to n equals 3. Infrared, the Brackett series to n equals 4, discovered by Frederick Sumner Brackett in 1922. Far infrared, all predicted by Bohr's formula. Astronomers use these series constantly. The H-alpha line at 656 nanometers dominates the spectra of emission nebulae. Regions of ionized hydrogen in space glow red because electrons recombine with protons and cascade down through energy levels, emitting H-alpha. The Orion Nebula's reddish-pink color, that's hydrogen. The Lagoon Nebula, hydrogen. The Rosette Nebula, hydrogen. Bohr's formula explains the color of star-forming regions across the universe. When you look at a Hubble photo of a nebula and see red, you're seeing the n equals 3 to n equals 2 transition in hydrogen atoms. You're seeing Bohr's quantum jump played out on cosmic scales. Spectral classification of stars depends on Balmer lines. A-type stars, like Vega, show the strongest Balmer absorption. Surface temperature around 10,000 Kelvin. Hot enough to excite hydrogen atoms into the n equals 2 state where they can absorb visible photons from the Balmer series. Cooler stars have most hydrogen in the ground state. Hotter stars have ionized hydrogen with no electrons to absorb. A-type is the sweet spot. Stellar spectra reveal temperature, composition, radial velocity through Doppler shift, rotation rate, magnetic fields, all traceable to quantum transitions, Bohr first explained. The Bohr radius, 0.0529 nanometers, defines the scale of atoms. Chemical bond lengths are typically 1 to 2 Bohr radii. Van der Waals forces operate over several Bohr radii. Molecular orbitals span multiple Bohr radii. This single number sets the size of chemistry. So why is the Bohr radius this specific value? Because it's determined by fundamental constants, Planck's constant, the electron mass, the electron charge, and the permittivity of free space. Combine them correctly and you get 0.0529 nanometers. Nature's constants fix the size of matter. The fine structure constant appears in Bohr's equations too. Alpha equals electron charge squared divided by 4, pi times permittivity of free space, times Planck's constant times the speed of light. Its value is 1 over 137.036. Dimensionless, universal. The fine structure constant determines the strength of electromagnetic interactions. It controls how tightly electrons bind to nuclei. Change alpha even slightly and chemistry breaks. Stars wouldn't shine. Life couldn't exist. Alpha's precise value makes the universe comprehensible. Bohr didn't invent alpha, but his model revealed its importance. Quantum mechanics grew from Bohr's work. Louis de Broglie proposed in 1923 that if light has particle properties, maybe particles have wave properties. He calculated that an electron's wavelength equals Planck's constant divided by its momentum. This hypothesis seemed crazy, but in 1927, Clinton Davison and Lester Germer diffracted electrons through a crystal. The electrons made an interference pattern. They behaved as waves. De Broglie was right. Particles are waves, waves are particles. Wave-particle duality is fundamental. Heisenberg's uncertainty principle from 1927 formalized the limits of measurement. You cannot simultaneously know a particle's position and momentum with arbitrary precision. The product of uncertainties is at least Planck's constant divided by 4 pi. The more precisely you measure position, the less precisely you know momentum. This is an experimental error. It's fundamental. The electron doesn't have a precise position and momentum simultaneously. Those properties don't exist together. Quantum mechanics isn't classical physics with measurement noise. It's a different kind of physics. Schrödinger's equation describes how quantum wave functions evolve. Solve it for hydrogen and you get orbitals. The 1s orbital is spherically symmetric. The 2s has a radial node. The 2p orbitals are dumbbell-shaped. The 3d orbitals have complex shapes. These aren't orbits. They're probability distributions. The electron is somewhere in the cloud. Where exactly? The question is meaningless until you measure. Then the wave function collapses and the electron appears at a specific location with probability given by the wave function squared. Measurement creates reality at the quantum level. Before measurement, the electron is genuinely in a superposition of all possible locations. Bohr and Heisenberg debated this interpretation throughout the 1920s. The Copenhagen interpretation, as it became known, holds that quantum mechanics is complete. There's no deeper reality beneath the wave function. The wave function is reality. Einstein disagreed. He thought quantum mechanics must be incomplete. God doesn't play dice with the universe. Bohr countered that Einstein shouldn't tell God what to do. The debate continued until Einstein's death in 1955. Modern experiments support the Copenhagen view. Quantum randomness is real. Hidden variables don't exist. Entanglement violates local realism. The universe is fundamentally probabilistic. Bohr was right. The Bohr model failed for multi-electron atoms but succeeded in revealing the quantum nature of matter. That's what matters. Scientific progress isn't about being correct forever. It's about advancing understanding. Bohr advanced understanding more than almost anyone in the 20th century. He showed that atoms follow quantum rules. He connected those rules to observable phenomena. He built the intellectual framework that enabled quantum mechanics. Without Bohr's bridge, we might have taken decades longer to reach modern physics. Every technology relying on quantum mechanics traces back to Bohr: semiconductors, transistors, integrated circuits, computers, lasers, LEDs, MRI scanners, atomic clocks, GPS satellites, solar panels, quantum cryptography, all depend on electron energy levels being discrete. All exist because Bohr figured out that orbits are quantized. The modern world runs on quantum mechanics. Bohr built the road. His personal life was marked by tragedy. His first wife died in 1909. His eldest son was killed in World War I in 1916. Both daughters died in childbirth. His home in Berlin burned after an air raid in February 1944. His second son was executed in 1945 for involvement in the plot to assassinate Hitler. Through all this, Bohr continued working. He rebuilt German science after World War II as president of the Kaiser Wilhelm Society, which became the Max Planck Society in 1948. His resilience was extraordinary. The simplicity of the Bohr model is deceptive. It feels like atoms must be this way, but there's no must about it. Nature could have been fundamentally different. Electrons could have had any energy in classical physics. They don't. No, energy is quantized. That's a fact about reality, not a logical necessity. Bohr discovered this fact by combining Rutherford's nucleus, Planck's quantum force, and the hydrogen spectrum. He didn't derive it from deeper principles. He guessed it, then he checked if the guess matched observations. It did. That's how physics works. Guess, calculate, compare. If your guess predicts new phenomena that subsequently get confirmed, your guess becomes a law. The correspondence principle links quantum and classical. At large quantum numbers, quantum behavior averages to classical predictions. An electron in the N equals 1 million orbit acts almost classically. Its energy levels are so closely spaced that jumps between them emit nearly continuous radiation. The quantum choppiness smooths out. Bohr understood that quantum mechanics must reproduce classical results in appropriate limits. This insight guided him through the maze of quantum paradoxes. If your quantum theory doesn't give classical answers for classical systems, it's wrong. Bohr's influence extended through his students. Heisenberg came to Copenhagen in 1924 at age 23 and developed matrix mechanics under Bohr's guidance. Pauli formulated the exclusion principle while corresponding with Bohr. George Gamow, later famous for Big Bang cosmology, worked at Bohr's Institute from 1928 to 1931. Lev Landau, Hendrik Casimir, Oscar Klein, Christian Müller, the list goes on. Bohr's Institute was the Harvard of quantum physics. Getting there was a career maker. Bohr's mentorship shaped a generation. The model's limitations are well known today. It doesn't explain chemical bonding beyond the simplest cases. It doesn't account for the Zeeman effect, splitting of spectral lines in magnetic fields, except partially. It gives the wrong ground state angular momentum for hydrogen. It predicts specific orbits rather than orbitals. It can't handle molecules except in crude approximations. The quantum numbers n, a, l, a, I, m that Bohr derived were correct, but the physical interpretation was wrong. Electrons don't orbit. They occupy standing wave patterns. The Bohr model was a stepping stone, not a destination, yet that stepping stone was essential. Before Bohr, quantum theory was a collection of strange rules, Planck's quanta, Einstein's photons, strange discontinuities nobody understood. Bohr unified them. He showed that quantum rules govern atoms. He made quantum mechanics a theory of matter, not just radiation. He turned abstract mathematics into physical reality. Atoms aren't little solar systems, but they are quantized. Energy levels are discrete. Spectral lines arise from quantum jumps. Bohr got the mechanism wrong, but the principle's right. That's enough. That's genius. In the grand arc of physics, the Bohr model marks the transition point. Before Bohr, physics was classical, Maxwell's equations, Newton's laws, thermodynamics. After Bohr, physics was quantum, Heisenberg, Schrödinger, Dirac. The revolution happened between 1913 and 1928. Bohr was there at the beginning, middle, and end. He proposed the first quantum model of the atom in 1913. He nurtured the development of full quantum mechanics in the 20s. He defended the Copenhagen interpretation against Einstein in the 30s. He spent 4 decades at the center of quantum physics. No one contributed more consistently. The trilogy itself, those 3 papers from July, September, November 1913, totaled 70 pages. The first paper alone was 25 pages. Dense, mathematical, revolutionary. Bohr sent drafts to Rutherford, who liked the ideas but thought the papers too long. Bohr shortened nothing. He needed that length to build his argument carefully, to show how quantum postulates resolve classical contradictions, to derive the spectral formulas, to extend the model beyond hydrogen. The length wasn't padding. Every page mattered. Reading the trilogy today, it's striking how much Bohr got right on first pass. He made mistakes. Claiming electrons in stationary states don't radiate was ad hoc, but the core structure holds. Quantized orbits, quantum jumps, energy proportional to frequency. These ideas survived. The community reaction was slow. Few physicists in 1913 immediately recognized the importance. Mosley did. Darwin did. Rutherford was supportive but cautious. Most ignored it. Quantum mechanics wasn't yet respectable. Bohr's assumptions seemed arbitrary. Why should angular momentum be quantized? Why those particular orbits? Where's the mechanism? Bohr had no answers. Just results that matched hydrogen's spectrum exactly. That's suspicious. Too good to be true. Except it was true. Every measurement confirmed it. By 1915, after Frank Hertz and Mosley, resistance crumbled. The Bohr atom became orthodoxy, practically overnight. Science doesn't progress smoothly. It lurches. Long periods of incremental refinement punctuated by sudden revolutions. Bohr's papers were a revolution. They didn't extend existing theory. They replaced it. Atoms don't follow Newton's laws. They follow quantum laws. This shift wasn't minor. It redefined physical reality. Before Bohr, matter was thought to be fundamentally continuous, with properties varying smoothly. After Bohr, matter is fundamentally discrete. Energy levels have gaps. Transitions are abrupt. Continuity is an illusion emerging from vast numbers of discrete events. Reality at the smallest scale is pixelated, not smooth. The philosophical implications troubled many. Einstein never accepted quantum mechanics, inherent randomness. Schrödinger disliked the discontinuous jumps. De Broglie worked for years trying to restore classical determinism. But experiments kept confirming quantum predictions. Bell's theorem in 1964 proved that no local hidden variable theory can reproduce quantum results. The EPR paradox that Einstein proposed in 1935 as a problem for quantum mechanics became evidence for quantum entanglement. Nature really is non-local. Measuring one particle instantly affects its entangled partner, regardless of distance. Bohr's quantum mechanics describes this correctly, even though it seems impossible. Bohr died the year Bell published his theorem. He never knew how thoroughly quantum mechanics would be vindicated. But he knew enough. Decades of experiments had confirmed quantum predictions. No rival theory came close. Quantum mechanics works. The universe is quantum. Classical physics is the approximation, not the other way around. Bohr saw this in 1913. It took physics 50 years to fully accept it. Today, we measure Bohr radii in experiments. We build quantum computers exploiting superposition and entanglement. We create Bose-Einstein condensates where atoms occupy the same quantum state. We trap single atoms in electromagnetic fields and watch them make quantum jumps in real time. In 2019, a research team at Yale observed a quantum jump happening and reversed it before completion. They caught an atom mid-jump and nudged it back. Bohr would have loved this. The quantum jumps he postulated in 1913 are now so well understood we can control them individually. The mathematical structure Bohr discovered, energy proportional to 1 over n squared, wavelengths following the Rydberg formula, extends beyond hydrogen. Helium ions with 1 electron show the same pattern scaled by the nuclear charge squared. Lithium ions with 2 electrons removed behave similarly. Any hydrogen-like ion follows Bohr's math with a scaling factor. The formula is universal for single electron systems. Multi-electron atoms require quantum mechanics, but the single electron case remains exactly soluble using Bohr's approach updated with Schrödinger's wave functions. The connection between Bohr's model and quantum field theory runs deep. When you quantize the electromagnetic field, photons emerge as excitations. When electrons jump between atomic states, they create or destroy photons. Emission and absorption are quantum field processes. The matrix elements describing these processes depend on the wave functions of initial and final states. Calculate those wave functions from Schrödinger's equation using hydrogen's potential, and you recover Bohr's transition rates. Modern quantum electrodynamics includes corrections for vacuum polarization and self-energy, but the leading order matches Bohr's results. His model captured the essential physics. Atomic spectroscopy, measuring emission and absorption spectra, became a primary tool for studying matter because of Bohr. Identify spectral lines, deduce atomic composition, measure line widths, determine temperature and pressure, observe line shifts, calculate velocity via Doppler effect, map spectral lines across astronomical objects, infer their structure and dynamics. None of this worked until Bohr explained what spectral lines mean. They're quantum transitions. Each line represents a specific energy gap. Record the spectrum and you decode the quantum state. Spectroscopy is quantum mechanics made visible. The Bohr model appears in chemistry textbooks because it explains valence qualitatively. Elements with full outer shells, helium and neon, argon, are inert. They don't react chemically because adding or removing electrons costs too much energy. Elements with 1 electron beyond a full shell, lithium, sodium, potassium, easily lose that electron to form positive ions. Elements 1 electron short of a full shell, fluorine, chlorine, bromine, easily gain an electron to form negative ions. Chemical bonding arises from atoms exchanging or sharing electrons to achieve full shells. This is oversimplified. Real chemistry uses molecular orbitals, but the shell picture provides intuition. Bohr's model underlies that intuition. The Manhattan Project scientists used Bohr's knowledge. Uranium-235 fissions differently than uranium-238 because their nuclei have different energy levels. Separating isotopes relies on tiny mass differences. Measuring those differences requires spectroscopy. Enriching uranium for bombs needed precise understanding of atomic behavior. Bohr contributed to this, though he opposed military use. The irony wasn't lost on him. His peaceful discovery of atomic structure enabled atomic weapons. He spent his later years advocating for arms control. Science is morally neutral. Applications are not. Every element's spectral fingerprint is unique. No 2 elements emit or absorb the same pattern of wavelengths. This allows identification of substances without direct contact. Point a spectrometer at a star and you know what it's made of. Analyze the spectrum of a distant galaxy and you measure its redshift, therefore its distance and recession velocity. Cosmology depends on spectroscopy. Bohr's explanation of spectral lines made the universe readable. The leap from classical to quantum required courage. Bohr abandoned the determinism that had governed physics for centuries. He accepted that atoms follow different rules. He trusted mathematics and experiment over intuition. Most physicists would have tried to save classical mechanics. Bohr recognized it was doomed. Classical mechanics works at human scales because quantum effects average out over enormous numbers of particles. At atomic scales, quantum rules dominate. Bohr saw this clearly in 1913 when most physicists were still hoping quantum theory would turn out to be a temporary oddity. The Bohr-Einstein debates at Solvay conferences in the late 20s are legendary. Einstein proposed thought experiments designed to show quantum mechanics violated energy conservation or causality. Bohr found flaws in each one, sometimes using Einstein's own relativity against him. The debates sharpened both men's thinking. They remained friends, despite fundamental disagreement. Einstein admired Bohr's genius, even while rejecting his interpretation. Bohr respected Einstein's insight even while defending quantum mechanics. intellectual combat at the highest level. Neither convinced the other. History vindicated Bohr. Quantum computing relies on Bohr's principle that atoms have discrete states. A qubit is a quantum system with two well-defined states, like the ground and first excited state of an atom. Superposition means the qubit can be in both states simultaneously until measured. Entanglement means multiple qubits can be correlated in ways classical bits cannot. Quantum algorithms exploit these phenomena to solve certain problems exponentially faster than classical computers. Factor large numbers, search unsorted databases, simulate quantum systems. All possible because atomic energy levels are discrete and atoms can be in superpositions. Bohr discovered the underlying physics in 1913. We're building computers on it a century later. The Bohr magneton, the unit of magnetic moment for atoms, equals electron charge times Planck's constant divided by 4 pi times electron mass. It quantifies how atoms interact with magnetic fields. MRI machines exploit this. Nuclear spins precess in strong magnetic fields at frequencies determined by the Bohr magneton. Apply radio frequency pulses at the resonant frequency, and you flip the spins. Measure the relaxation, and you map tissue density. Medical imaging exists because Bohr figured out atoms are quantized. Atomic clocks use quantum transitions. Cesium-133 atoms have a hyperfine transition at exactly 9,192,631,770 cycles per second. By definition, a second is this many cycles. GPS satellites carry atomic clocks. Your phone receives signals from multiple satellites and triangulates position based on signal timing. The system requires nanosecond precision. Relativity matters. Time runs differently at orbital altitude. Quantum mechanics matters. The cesium transition defines time. Bohr's atomic model ultimately enables GPS. The Nobel Prize in 1922 recognized Bohr's achievement. The citation praised his investigation of atomic structure and radiation. By then, Bohr's reputation was secure. Copenhagen was the quantum mechanics capital. Young physicists flocked there. Bohr organized weekly discussions where every idea was questioned ruthlessly. He fostered an environment of intense intellectual exchange. Disagreement was encouraged. Certainty was suspect. The Copenhagen spirit of questioning assumptions influenced physics for decades. The final truth about Bohr's model is that it was wrong in specifics, but right in essence. Atoms aren't miniature solar systems. Electrons don't orbit like planets. But energy levels are quantized. Transitions between levels emit photons. The hydrogen spectrum arises from quantum jumps. These insights survived the transition to wave mechanics. The Bohr radius is still the natural length scale for atoms. The Rydberg constant still governs hydrogen spectroscopy. The quantum numbers N-LAM still label atomic states. Bohr's model was wrong and right simultaneously. Wrong mechanism, right predictions. In science, that's often good enough to spark a revolution. Modern quantum mechanics textbooks derive the hydrogen spectrum using Schrödinger's equation and get the same energies Bohr calculated with his circular orbits. The math evolved, but the physics stayed constant. Energy proportional to -1 over n squared. Ground stayed at -13.6 electron volts. Spectral lines following the Rydberg formula. Bohr had the correct physics from the start. His interpretation just needed updating when wave mechanics arrived. The core remained. That's how you know Bohr was onto something fundamental. His specific model fell apart quickly. Sommerfeld patched it in 1916. Heisenberg replaced it in 1925. But the quantum principles Bohr articulated, energy quantization, stationary states, quantum jumps, are still true. They're embedded in modern quantum mechanics. Every quantum mechanics textbook starts with Bohr. Then it improves on Bohr. But it starts with Bohr because Bohr got the quantum nature of atoms right for the first time in history. In 2013, CERN celebrated the centenary of the Bohr model with an article in CERN News published that July. They called it The Birth of Quantum Theory. Planck had quanta. Einstein had photons. But Bohr had quantum atoms. He showed that matter itself follows quantum rules, not just radiation. That was the conceptual leap that made quantum mechanics a complete theory of nature. Without Bohr, quantum theory might have remained a curious feature of light. With Bohr, it became the foundation of physics. The trilogy papers, sitting in the archives of Philosophical Magazine from July or September, November 1913, represent one of the great intellectual achievements of the 20th century. 27-year-old Bohr recently arrived from Denmark, working out how atoms actually function, not how they should function according to classical theory, how they do function according to nature, observation over theory. Experiment over intuition. That's the scientific method at its purest. What changed between Rutherford's nuclear atom in 1911 and Bohr's quantum atom in 1913? One insight. Electrons can't spiral inward because energy levels are discrete. There's no continuous path down. Classical physics demands continuity. Quantum physics is fundamentally discrete. Bohr saw this. He didn't have a mechanism. He just knew it had to be true because hydrogen's spectrum is discrete. If the energy levels were continuous, the spectrum would be continuous. It isn't. Therefore, energy levels aren't continuous. Simple logic. Revolutionary conclusion. The spectrum of hydrogen has been measured with extraordinary precision. The H-alpha line is at exactly 656.28 nanometers in vacuum. Not 655, not 657, 656.28. The precision is ridiculous. 9 significant figures, and Bohr's formula, using 2 fundamental constants, predicts this wavelength correctly. The agreement isn't approximate. It's exact to within experimental error. That's not luck, that's physics. When your theory predicts measurements to 9 decimal places, you've discovered something true about reality. A recent research paper published in the Proceedings of the National Academy of Sciences in 2005 revisited Bohr's molecular model. Turns out it works better than previously thought for simple molecules like hydrogen gas. The paper found previously undescribed solutions within Bohr theory that describe the hydrogen molecule's potential energy curve almost as well as early wave mechanics. Bohr's model, applied cleverly, gives surprisingly accurate molecular binding energies. It shouldn't work. It's not quantum mechanics. But it does work because Bohr captured essential quantum behavior with his discrete orbits. Sometimes, wrong models give right answers when they encode correct principles. The genius of understanding atoms the way Bohr did was recognizing that nature doesn't care about our equations. Classical mechanics is elegant. It's consistent. It's been tested for centuries. And it's wrong at atomic scales. Nature isn't obligated to follow our mathematics. We have to discover nature's mathematics. Bohr did that. He discarded classical mechanics where it failed. He imported quantum concepts where they worked. He built a hybrid model that made accurate predictions despite violating every classical principle. That's genius, not refining existing theory. Creating new theory, when existing theory fails catastrophically. The way Bohr understood the atom in 1913 was much more genius than most people imagine, not because he got everything right. He didn't. But because he got the fundamentally important things right, quantization, stationary states, quantum jumps, while everyone else was still clinging to classical mechanics, he saw past the equations to the physics underneath. Atoms follow quantum rules, period. Figure out those rules, whatever they are. And that was Bohr's approach. It worked spectacularly. The hydrogen spectrum proved it. Frank Hertz confirmed it. Mosley validated it. Within 2 years, Bohr's model was physics fact. In the Manchester Physics Laboratory basement, where Mosley conducted his X-ray measurements, researchers recently discovered notes in Mosley's handwriting from September 1913. The notes mentioned Bohr explicitly. Mosley wrote that he was testing Bohr's theory because if Bohr was right, atomic number equals nuclear charge exactly. Not approximately. Exactly. Mosley's measurements confirmed this. His X-ray data matched Bohr's prediction of discrete energy levels in atoms, the first physical evidence beyond hydrogen. Mosley knew he'd found something momentous. He wrote to Bohr describing the results. Bohr was initially puzzled about details, but realized quickly that Mosley had experimentally verified quantum atomic structure. That letter exchange in late 1913 between Copenhagen and Manchester was a turning point. Theory met experiment. Both confirmed the other. We stand on Bohr's shoulders now. Every quantum technology, every atomic measurement, every spectroscopic analysis, every understanding of chemical bonding, every particle physics experiment, every quantum computer algorithm. Bohr's 1913 insight that atoms are quantum systems propagates forward through all of it. The modern world runs on quantum mechanics. Quantum mechanics began with Bohr's atom. That's the way Bohr understood the atom, not as classical objects shrunk down, as quantum systems with discrete energy levels. He didn't have wave functions. He didn't have operators. He didn't have Hilbert spaces. He had hydrogen spectrum and the courage to say classical physics doesn't apply here. We need new rules. He wrote those rules in 3 papers totaling 70 pages published in summer and fall 1913. Those papers changed physics forever. The hydrogen atom went from inexplicable mystery to solved problem. The quantum revolution went from speculative idea to established fact. The archive at the Niels Bohr Institute in Copenhagen contains over 10,000 documents from Bohr's career. Letters to Rutherford, calculations for the trilogy papers, correspondence with Mosley, with Einstein, with Heisenberg. Drafts showing how Bohr's ideas evolved. The transition from classical thinking to quantum thinking documented in real time. Reading those papers today, you see a brilliant mind grappling with reality's quantum nature, making false starts, backtracking, trying different approaches, finally hitting on stationary states and quantum jumps. Then the mathematics flows and the hydrogen spectrum appears. That moment, when Bohr realized the Rydberg formula followed from his quantum postulates, must have been electric. Everything clicked. Balmer's empirical pattern became a theorem. Spectroscopy became comprehensible. Atoms made sense for the first time since antiquity. The distance between not understanding atoms in 1912 and understanding them in 1913 is vast. Bohr crossed it in months. Working at a blistering pace in the first half of 1913, he formulated quantum postulates, calculated hydrogen energies, derived the Balmer formula, extended the model to ionized atoms, discussed molecular formation, explained the periodic table structure, and wrote 3 papers totaling 70 pages presenting all of this. That's not normal productivity. That's genius working at full intensity. Bohr saw the answer and pursued it relentlessly until he'd worked out the implications. The result was atomic physics. Before Bohr, atoms were mysterious. After Bohr, atoms were understood. Still strange, still quantum, but understood. In the CERN archives, historical documents section Tong, stored in a temperature-controlled vault, sit the original issues of Philosophical Magazine from 1913. July, September, November, Bohr's trilogy. The papers that birthed modern physics. Yellowed now, fragile, priceless. Those pages contain the first correct description of atomic structure, the foundation of quantum mechanics, the beginning of chemistry's quantum explanation, the start of solid-state physics, the origin of lasers, semiconductors, nuclear power, all modern electronics, contained in 3 papers by a 27-year-old Danish physicist who'd spent 6 months in Rutherford's Manchester lab and returned to Copenhagen determined to figure out why atoms don't collapse. He figured it out. The universe is quantum. Bohr proved it.